Hey everybody, we are here with another live office hours. I'm partnering with Chegg to bring you help with Organic Chemistry 1 every Tuesday at 5 p.m. PST. So today we're going to be going over, as usual, some organic chemistry practice problems, some ones that I've put together that I think will be roughly matched with where you're at in the semester, ideally. Please go ahead and check out the QR code in the corner, on the top left corner, if you want to see all the different office hours that Chegg is offering. You can get help with math and all kinds of other classes that you're taking. But once again, we will be going over Organic Chemistry 1 practice problems, as we have been doing for quite a few weeks now at this point. So the chat is open. Live chat is ready for you guys to feel free to ask any questions. They can pertain to the questions that I'm going over that I've prepared, or they can be other unrelated Organic Chemistry 1 questions. But please, let's keep them topical. Let's keep them within the Organic Chemistry 1 framework. That is the purpose of this live stream. So we will, let's just go ahead and get started now. If you will recall, last week we moved on from addition reactions. We were going over ozonolysis, Diels-Alder, some different kind of reactions. So we're going to review some more of those today. And then hopefully, if we get to the end of this one, we'll start doing a little bit of spectroscopy. I've got an NMR question for you. And then also getting into some electrophilic aromatic substitution reactions. That is a very, very big unit that usually comes pretty soon after some of these other reaction classes that we've been going into. So let's go ahead and get started. This one should be a review from last time. So draw the reactants that would yield these products. And here are the conditions. So this is what we're going to get. And this is how we got there. So what this is one of your flashcard reactions, right? We need to have this on one side of a flashcard, and on the other side, it's going to say ozonolysis, right? Ozonolysis. What does ozonolysis do? Ozonolysis cleaves pi bonds, cleaves carbon-carbon pi bonds, and yields carbonyls. So if in the forward direction, ozonolysis takes the two carbons that were participating in the carbon-carbon pi bond, and it cleaves that, and then those two carbons are now carbonyl carbons. If we're going in the reverse direction, if we're thinking retrosynthetically, all we have to do is take the two carbonyl carbons and smush them together and put a pi bond between them, put a double bond between them. So we get rid of the oxygens, and these two carbons now have a double bond between them. So let's do that. We've got the 5-membered ring, and then we have this 1, 2, 3, 4 carbon group, right? We are going to go double bond to this carbon, and now that carbon is connected to an isopropyl group, right? So that is going to be what we get. I would say probably the most common error here would be to have this carbon be the start of the isopropyl group, right? So we would just have 1, 2 carbons there. We would be missing a carbon though, right? We have 1, 2, 3, 4, 5, and 1, 2, 3, 4. So we have to have these 5 carbons. The other fragment has to have 4 carbons. We're not going to gain or lose any carbon content. All we're doing is if in the forward direction, we cleave this, right? In the forward direction, we cleave this double bond, pull those fragments apart, and the two carbons that were participating in the double bond now have carbonyls on them. And this is this type of workup is going to ensure that we end up with an aldehyde rather than carboxylic acid. So this is the way. That's it, right? Let's get rid of that red line. This is going to be the reagent, and again, all we did was we took the two carbons that now bear the carbonyls in the product, got rid of the oxygens, smush them together, and put the double bond between them. Okay, so that's that one. See if I missed anything. Un grande grazie per tutto quello che fai. Grazie. Prego. Can we please go over SN1 and SN2 reactions? So, Tatiana, I actually spent probably the third and fourth sessions predominantly on SN1, SN2. So I don't have any of those today because that's really that's the first reaction class that you go over is substitution and elimination. But if you go to my channel and you go to the live tab, you can see all of these office hours that I've been doing for Chegg, and you can find the ones that were covered SN1, SN2. So yeah, so please check dozen problems on those reactions there. K Bay says, can you go over some aldehyde and ketone reactions? So that would be like enolate chemistry. We do have a little bit of enolate chemistry in this worksheet, so we will get to those. Ukiyo says, do you recommend taking OChem for people going into med majors? You have to. I am not aware of anybody going into any medical field that does not have to take organic chemistry. It should be mandatory, and for good reason. If you don't understand how molecules work, it's going to be difficult to work in any medical field. Very important. Yep. Okay, so let's move on to the next one here. So here's just an addition reaction with a little bit of a twist here, because we have this conjugated polyunsaturated system. So it's polyunsaturated. Each of these pi bonds is a degree of unsaturation, and it's polyunsaturated because there's more than one, right? So two of these makes it polyunsaturated, and it is conjugated because we have a double bond, single bond, double bond, right? When it's alternating double bond, single bond, double bond like that, we call it conjugated, and the reason is because it affords the potentiality for resonance. So resonance means the delocalization of pi electron density, and when pi bonds are conjugated, they can delocalize. So let's see what happens. This should be a regular addition reaction, right? We have HI, and so what are we going to do? Just like a normal addition reaction, let's pretend that there's only one pi bond. Let's have that pi bond react. Let's take this one over here. So that pi bond is going to act like a nucleophile. It is going to get the hydrogen there, and then these electrons will stay with iodine to form the iodide anion, and we are going to get this. So this pi bond will still be here, and we have a carbocation here. Now, this is a very important aspect of the regiochemistry to get to the intermediate. We know that if this other pi bond were not there, then we could be getting the carbocation on either carbon, because both carbons are secondary, right? So Markovnikov and anti-Markovnikov don't really apply here, right? We know that if this was the substrate, right, then we know that we would be getting the secondary carbocation over the primary, because it's more substituted. So that would dictate that here, that in that case. But here we don't have that, right? We have two secondary carbons. But if we have the carbocation in this position, it is conjugated. It is in the conjugated position with this other pi bond, which allows for resonance. So what is the other resonance structure? If we take this pi bond and we go over there, so if this pi bond moves over there, it's going to neutralize this carbocation, right? Right now, this carbocation has only 3 electron domains. It's got these 2 carbons and 1 implied hydrogen, but it wants 4. That's why it's got a plus charge. If it receives this pi bond, it's receiving one of the electrons in the pi bond. It will neutralize. But then then this carbon over here lost an electron domain. So now we have a carbocation over there, right? If this pi bond goes over here, this carbon is losing an electron domain. So now the carbocation is over there. So truly the composite resonance structure looks like this. It's got partial pi electron density. Let me make this a little bit bigger, actually. We've got partial pi electron density and a delocalized positive charge, right? The delocalized positive charge is all around. It's distributed. It's delocalized around these 3 carbons, right? So that's the composite. That's what the molecule actually looks like. But we can use these resonance structures to continue the mechanism. So what else is in solution? Remember, we generated an iodide ion in the first step. We grabbed that proton, generated an iodide ion. So what can iodide do? Let's have iodide attack. we have a negatively charged iodide ion, and we have a positively charged carbocation. They'll react, right? That's very obvious. Minus meets plus. So that goes there. And so here, now here's the thing. This is an sp2 center. So we need to think about stereochemistry. This is trigonal planar, right? When a carbon or any atom has 3 electron domains, that's going to be trigonal planar, right? sp2 hybridized, 120-degree bond angles. So that means that an incoming nucleophile can approach from either side. So we're actually going to get 2 isomeric products here. So the pi bond will still be there, but we're either going to get the iodide on the wedge or the iodide on the dash, right? So that's if iodide attacks here. But don't forget, we have another resonance structure. The iodide could just as well attack this other resonance structure. So what if it attacked that one? Then again, we're going to get 2 products because this is an sp2 center. It can attack from this side, it can attack from this side, and it will do so with identical probability, 50-50. So on the macroscopic scale, you have quadrillions upon quadrillions of molecules reacting. Statistically speaking, it's going to be 50-50. So that's called a racemic mixture. So we are going to get... we can have the iodo group here, or we can have the iodo group here. So there are 4 products. There are 2 structural possibilities, but each of them has is a racemic mixture of enantiomers. So we have 4 products possible. Now, bear in mind that's because this molecule is symmetric, right? If it was not symmetric, then you would have even more products because all we did was react this pi bond. But what if we reacted the other pi bond? Well, if we reacted the other pi bond, we would have the carbocation right there, and it actually would be that just flipped over on the other side. So the symmetry of the molecule dictates that we don't even have to look at the other pi bond. But if we just added one more methyl group right there, right, one more carbon right there, now the molecule is not symmetrical anymore. You would have 4 products if this pi bond reacts, and you'd have another 4 products if this pi bond reacts. So it gets pretty messy with these conjugated polyunsaturated systems because of this resonance, right? You get the pi bond reacts, you get a carbocation, but it is delocalized. It can be pushed around to another atom, another carbon atom because of that other pi bond there. And so you can get different structurally isomeric products. So that is a very simple addition reaction, but done on a conjugated polyunsaturated system, which makes it a little bit trickier. Okay, let's see if I missed anything. Okay, hit that. Isyane says, can you make exercises about primary, secondary, tertiary structures and how they're bonded, please? So that's just about how many carbons, right? So like, okay, here is, for example, okay. So when we say primary, secondary, tertiary, quaternary, what are we talking about? We're talking about the how many carbons are bonded to the one in question. So for example, these are all primary carbons because they're all bonded to one other carbon, right? So that's primary. Secondary is bonded to 2 other carbons. So that would be that one, right? So this carbon is bonded to that one and that one. So that's a secondary carbon. Do we have more colors here? Just that? Let's do black. So tertiary would be if it's bonded to 3 carbons. So that would be that one because it's bonded to 1, 2, 3 carbons. And then quaternary, I guess just do blue. Quaternary is if it's bonded to 4 other carbons. So I'll put a little box around that one. So this is bonded to 1, 2, 3, 4 other carbons. That's the most other carbons that it can be bound to. So primary, secondary, tertiary, quaternary, that's what we're talking about. And then when we say secondary alcohol, right? If we say like a secondary alcohol, this would be a secondary alcohol because the carbon that bears the hydroxyl is a secondary carbon. Right. You can have a tertiary alkyl halide. You can have a primary alcohol, right? That kind of stuff. So that's what those words mean. Okay. Yeah, people asking if you can react the second pi bond. Yes, if you have HI in excess, of course that can react again. So can get we were just doing one addition reaction, but it can continue. Okay, let's do the next one. So now let's look at a Wittig reaction. So I don't think that we talked about Wittig last time, but Wittig is a great strategy for synthesizing alkenes, and they can be synthesized from a carbonyl containing compound and what's called a Wittig reagent. So this is a Wittig reagent, and it is what we notice is that we have a carbanion connected to a triphenylphosphine with a positive charge. So there's another resonance structure that just has the pi bond here. But it's a little, for quantum mechanical reasons, this actually dominates, even though there are two formal charges as opposed to all neutral atoms. But also it helps us understand mechanistically what's going on. This is a source of nucleophilic carbon. Remember, just like a Grignard reaction, a Grignard reagent is a source of nucleophilic carbon. Because the carbon is more electronegative than the magnesium atom that it's bound to. This is a source of nucleophilic carbon because there's a resonance structure in which it has a formal negative charge. So the negatively charged carbon attacks the carbon that right. We already know that carbonyl carbons are electron deficient, right? They're partial plus. So the nucleophilic carbon on the Wittig reagent attacks the electrophilic carbon on the ketone, and we end up with a double bond between them. So boom, and then boom, 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 boom. So we have our 5 carbon fragment over there, and 1, 2, 3, 4, 5 carbon fragment over there. So this carbon, when you're doing a Wittig, the negatively charged carbon on the Wittig reagent and the carbonyl carbon now have a double bond between them, right? That's how Wittig works. It goes through a 4-membered ring, intermediate, and then snaps shut, kicks off the other fragment, and we get that. So that is Wittig. Wittigs make alkenes, right? For all of these reactions, it's definitely important to remember what they produce. So like, for example, Grignard makes alcohols. We know that. If we're trying to do Grignard and the product does not end up as an alcohol, something went wrong, right? Grignards make alcohols. Likewise, Wittig makes alkenes. That's what it does. So that's it. Parasitic Wasp asks, is the topic chosen or can you give suggestions? So I prepare these just so we have a lot to talk about. Also because with organic chemistry, it's important to have structures drawn to be able to do examples. But feel free to ask questions. I can either elaborate on what I'm talking about here, or like, for example, a second ago, somebody asked me about primary, secondary, tertiary, quaternary. If it's something that simple, I can just draw something really quick and talk about it. So I totally will take a tangent if you have a question that is very easy to answer in a brief tangent. Some people have entire topics they want explained. I just take those into account. I try to include them in the presentation the following week. But definitely feel free to ask questions, and I will try to cater to those. Okay, let's move on. So earlier, somebody was asking for ketone and aldehyde stuff. So this is enolate chemistry. So there's a whole class of reactions that deal with the generation of enolates. And and so we're talking about aldehyde, ketone and aldehyde substrates. There are other reactions that work on esters as well. And so what's going to happen? So the first thing that we understand, Rio says, how do we know it's Wittig? We know it's Wittig because there's a Wittig reagent, right? This right here is the tip off. This is the important functional group on the Wittig reagent. That's that. Okay, so now we have an aldehyde, right? We have ethanol, and we're doing this in strong base. We've got sodium hydroxide. So we have a strong base. A base is probably going to try to do an acid-base reaction. So it's going to try to react with the most acidic proton. Do we have any acidic protons on this aldehyde here? So we don't have any especially acidic protons, but we do have to understand that protons on a carbon that are alpha to a carbonyl are mildly acidic. So we have a few protons. Let me do that in pink, actually. We have a few protons on this methyl, right? We have 3 implied hydrogens. And these have a pKa of around 9. I'll write that right here. Sorry, not 9, 19. pKa of around 19, which is not especially acidic. It's about 1,000 times less acidic than water. So it's not very acidic, but hydroxide is a very strong base. So what hydroxide is able to do is go ahead and get one of those protons. Let's take that one. Can be any of them. And we're going to form this double bond here, and we're going to kick that up there. So this is called an enolate. Now, what's important to understand about an enolate, we have 2 resonance structures. Right? We have the resonance structure with the negative charge on the oxygen, and we have the resonance structure with the negative charge on the carbon. Now, the resonance structure with the oxyanion is more strongly contributing, right? We know that there can be multiple resonance structures, and they do all contribute to the composite resonance structure, but some can be more strongly contributing than others. And it happens to be the case that a more electronegative atom has a greater capacity to accommodate a formal negative charge. So oxygen, being more electronegative than carbon, can better accommodate a formal negative charge. So this, it's not wrong to draw enolates like this in your mechanisms. I prefer to draw it like this because it is truly more strongly contributing. So when I do, this is aldol condensation. This whole reaction is called aldol condensation. I like to draw my enolates like this because it's more representative of reality. However, what we need to understand is there is one resonance structure with carbon with a formal negative charge. So much like Grignard reagents, much like Wittig reagents, enolates are a source of nucleophilic carbon. It's specifically the carbon that is alpha to the carbonyl. All right, alpha just means 1 away. So here's the carbonyl carbon. Alpha means 1 over. So once we reacted that aldehyde with strong base, we got the enolate. The enolate is the source of nucleophilic carbon. And now, so what is it going to attack? So an enolate is a source of nucleophilic carbon. An aldehyde is a source of electrophilic carbon. The carbonyl carbon on the neutral aldehyde is electrophilic. So we know that nucleophiles can attack carbonyl carbons. We've known that already for a while. So why don't we have this attack another equivalent of the aldehyde? So let's have this go boom, boom, boom. And we will get right. So what is the new bond we got is right here. Whoops. Right there. See, that's the new carbon-carbon bond we got because the alpha carbon, right? This fragment was the enolate, but the carbonyl reforms and kicks this pi bond off. So this is the bond. This attacked, right? This attacked the carbonyl carbon. So this used to be the aldehyde, but it got attacked, and then kick that pi bond up there, and we have that. And so now we're going to just shuffle some protons around. So from water, right? Let's just have this. I'm going to run out of room here, but we can grab this from water. Let's go. Boom, boom. We have some water lying around, and that will protonate. And then now we're used to hydroxyl being a bad leaving group, but we're in very strong basic conditions. So we have a lot of hydroxide floating around in solution. So one more is not going to hurt. So in strongly basic conditions, we actually can get hydroxyl to leave. So let's go ahead and do this, and then this, and then this. I can do that a little better. All right. So there is our product. So this is the product of our aldol condensation. So once again, the protons on the carbon that are alpha to a carbonyl, whether it is an aldehyde, a ketone, even an ester, are just acidic enough, pKa around 19, to be abstracted by a strong base like hydroxide, and we're going to generate our enolate anion. Enolate anion has two resonance structures, one with the oxy anion, one with the carb anion. The oxy anion is more strongly contributing. Nevertheless, it is a source of nucleophilic carbon. Enolates tend to attack carbonyl containing compounds. So in this case itself, right, we just have two equivalents of ethanol. They can attack other things. There are instances in which they can attack alkyl bromides and alkyl halides and things like that. But here, the classic for aldol condensation, you can have it can react with itself, or you can have crossed aldol. So you can have two different aldehydes, or an aldehyde and a ketone, and then honestly you get kind of a mess of products because there's a lot of different combinations there. But here, all we have is ethanol, so it's going to attack ethanol. So it goes boom, boom, boom. Kick that pi bond up there. Get the oxy anion. Let's quit. We're in aqueous. This is aqueous strong base. So grab that. We're going to just protonate the oxy anion, and then another equivalent of base. Also heat. Right. This is driven by heat as well. This second step. The first step is aldol addition. And then the second step is the condensation. So the condensation is where we lose water. So we lose a proton, right? Let me do it in black. We lose a proton and a hydroxyl. So that is, we say, minus H2O. That's the condensation part. And so we get to our aldol condensation products. They're always going to have a carbonyl, because when the enolate attacks, it reforms the carbonyl. So the aldol condensation product has to have a carbonyl, and it has to have a degree, an alpha beta degree of unsaturation. So alpha means next to the carbonyl. Alpha in general, not just the carbonyl. That's a relative terminology that regards any functional group. So 1 away is alpha, 2 away is beta, 3 away is gamma, 4 away is delta. That's just the Greek alphabet, right? So alpha, beta, degree of unsaturation, that's going to be in there if it's an aldol condensation product. So this unit definitely confuses some students, but you really just got to work with the enolates, enolizing, having it attack, do the condensation, make it work. Okay, so let me just check the questions real quick, and then I think we're going to do a brief commercial. Let me just see. Chuku says the Wittig reagent is called an ylid, right? Yes, it is called an ylid. An ylid is a Zwitter ion. So a Zwitter ion has a positive and negative charge in the same molecule, and an ylid is a subset of Zwitter ions in which the positive and negative charge are on adjacent heteroatoms. Heteroatoms means not the same element, and adjacent meaning next to each other. So on the Wittig reagent, you had a carbanion next to a positively charged phosphorus. So that is an example of an ylid. That's correct. Yakim, I believe, says how to know whether a substance is an electrophile or a nucleophile. So nucleophiles will have formal negative charges, partial negative charges, right? A nucleophile has electron excess. Electrophiles have electron deficiency. They have a formal positive charge or a partial positive charge. So that's how we know. Electrophile, from Greek, loving electrons. So electron density attacks electrophiles because electrophiles love electrons. Yeah, Chukwu, the chemistry of enolates occurs on the alpha carbon. So not really electronegativity. It just, see, on this enolate, the alpha carbon, there's a resonance structure where the alpha carbon has a formal negative charge. So that is why. Okay. Orest says, no, yeah, so we can, when you have aqueous conditions, when you have basic aqueous conditions, the allowed species are hydroxide and water. When you have acidic aqueous conditions, you can have water and hydronium. So there's, you can grab protons from water, or you can protonate water, depending on whether it's basic or acidic. So that's fine. It's just a quick grabbing a proton from what's in solution. No problem. Okay, so we are all set with that one, and I believe we're going to do a very brief commercial. So let's go ahead and go to that.
And stressful and exciting.
I meant you.
Ooh, spicy. I like you already.
Okay, so what? You have the answers?
Do you just want the answers? Or do you want to learn?
All right. Let's get weird.
Get a grip on college with Chegg.
Okay, we are back. And so I missed a question here. Rio says, how do you know if a molecule is strong or weak nucleophile and strong or weak base? So really you become familiar over time, but it's just, it's case by case. So like, for example, hydroxide is a very strong base because oxygen has a formal negative charge. And something like an amine is less basic because it's a lone pair on a neutral nitrogen. So formal charge versus neutral atom, that's one trend. There's also like ionic radius. So like going down the halogens, going down the periodic table for the halide ions, fluoride, bromide, chloride, bromide, iodide, those become weaker bases because they can better stabilize the negative charge around a more diffuse volume. There are many different trends. So you kind of have to just familiarize yourself with the various trends in acidity and basicity based on different aspects of structure. Chukwu says alpha halo esters can also be reduced to form. Yeah, so there's, ester substrates can also undergo different kinds of enolate chemistry. Those are Claisen condensation and Dieckmann condensation. And yeah, okay, all caught up. So let's go back. Okay, so let me erase a little of this. So we got some room. Let's go back to Diels-Alder. So Diels-Alder is a really fun one. And we definitely have to be really good at going at Diels-Alder in either direction, forward or reverse direction. So this one's pretty standard. We've got our diene. We've got our dienophile. And let's be very clear about where the new bonds are going to form. So remember, the 6 carbons that are participating in the pi bonds, that's where all the chemistry is going to happen. So Diels-Alder goes from 3 pi bonds to 1 pi bond and 2 sigma bonds. So in the diene, and this is all concerted, right? So here I'm going to draw the arrows. So this pi bond goes here. This pi bond forms this sigma bond, and this pi bond forms this sigma bond. And this is happening in concerted fashion. So it's not the case that one pi bond is kicking another pi bond. It's not like a domino effect. This is all happening all at once, right? It is concerted, they say. So we're always forming a 6-membered ring with a Diels-Alder reaction. So when you're drawing your Diels-Alder product, always, always, always just draw a 6-membered ring, right? We will worry about what is on that 6-membered ring after, but we know for a fact that this 6-membered ring is there. If you're drawing a Diels-Alder product and you don't have a 6-membered ring, something went wrong. We know that we have a 6-membered ring. That's what Diels-Alder does. So here's our 6-membered ring. These 4 that were on the diene are there, and then these 2 that were on the dienophile are there. So what are they attached to? Well, first of all, we got to get that pi bond in there, right? We got 2 new sigma bonds. That's this one and this one. But we have a new pi bond there too. Now, is there anything else? On the diene, there's not. The diene, there are no other functional groups. On the dienophile, we have these 2, excuse me, we have these 2 other methyl groups. Now, how are we going to draw them on the product? Well, this dienophile is cis, right? We have a cis 2-butene. So these methyls are cis to one another. So they will be cis to one another on the product. Now we do not have to worry about stereochemistry here. If we drew those on the dash bonds rather than the wedge bonds, you flip it over, it's the same thing, right? Pick this up and put it on its other face. All of a sudden, the methyls will be on dash bonds pointing down instead of up. So, and that's because it's a meso compound, right? Meso. So no enantiomer, right? It's an achiral molecule. But we definitely have to know with Diels-Alder, first of all, we're forming a 6-membered ring. So these are the 2 new sigma bonds right there. Those are the new sigma bonds that formed in this cyclization. And then we just have to know a few things about stereochemistry. These were cis, so they're cis on the product. Okay, let's try one more. Okay, another Diels-Alder. So again, we're making a 6-membered ring. Always just draw the 6-membered ring first, then figure out what else there is. So what do we have? And let's go ahead and do the mechanism again. So this pi bond goes there, this pi bond goes there, this pi bond goes there. And these 2 carbons here don't participate, right? Sometimes students are a little confused when the diene is already cyclic, but it's actually okay, right? Just there's 2 other carbons there, but no chemistry happened there. They're still there, so we didn't lose them. We with these kinds of reactions, we're never ever gaining or losing carbon content. So you have to make sure it's all still there. But what actually happened, right? We have a pi bond there. Now, these 2 carbons are still there. There is still a 6-membered ring that these 2 carbons are participating in. Right? So we have these bridgehead carbons, and so it's a bicyclic structure. So these carbons are participating in multiple rings. Right. So we have a 1, 2, 3, 4, 5, 6-membered ring there, and a different 6-membered ring, which is the one that we formed in the Diels-Alder reaction. And then now again, we have these groups here. So the dienophile is cis, and so the product, these groups will also be cis. We have these 2 carboxyl groups that are going to be cis. Now here, I'm going to put them on the dash bonds. So now it does matter, right? Because we have this part of the ring is projecting up. So sterically, there is a difference between these groups projecting up with the ring or down away from the other ring. And so this, what we've drawn is the endo product, right? So you can have endo and exo products. Endo tends to dominate. There's a lot of different scenarios. And so endo usually dominates. There are ways to force it to go exo. So we won't get into tons of details there. But in this case, we're going to draw the endo product. And so that's got these going this way. But they must be cis to one another. So you could draw, like you will, if you drew the exo product, that wouldn't be wrong. You're just drawing the minor product, right? You will get some of that. But if you drew these group trans to one another, that violates the stereochemistry of the Diels-Alder. We're not going to get the trans product, right? You're not going to get one wedge and one dash. You're going to get both dash or both wedge. So here the dash gives you the endo product. So that's that one. Okay. Okay. Moises says, would this Diels-Alder reaction work with a trans configuration for the diunifial? Yes, it would. And in that case, the product would be, you would get a racemic mixture. So probably you're talking about that. So like if we had this diunifial, yes, absolutely. And we would get we would get a racemic mixture. We would get this guy and this guy. Very good question. Yes, correct. Ford asks, what level college class is this? This is Organic Chemistry 1, typically taken sophomore year of undergrad. That's when most people take it. Okay, let's move on. So let's do a little more enolate chemistry here. Now, we learned about the aldol condensation. Now we're going to talk about Michael addition. Okay, so the only difference with the Michael addition is that the thing that the enolate attacks. So first, let's enolize something. And so we have two carbonyl containing compounds, and we have strong base, right? We have hydroxide in there. And so where are we going to enolize? Well, this is pretty easy because this guy is not enolizable, right? Here's the carbonyl carbon. Remember that is the alpha position that has mildly acidic protons. And so this alpha position on this side, there's a phenyl ring there. So there is no implied hydrogen on this carbon, right? This carbon has 4 bonds to other carbon, the carbonyl carbon, and then 3 bonds to other carbons in the benzene ring. So there's no proton there. There is a implied hydrogen here, but it's not very acidic. It's way less acidic than a normal alpha proton, because if that were to enolize there, you would end up with accumulated diene, which is not favorable, right? It's just not a good situation to have a double bond here and then another double bond there. So this ends up, this alkenyl proton, even though it's in the alpha position, is dramatically less acidic than if we go over here. Here we have our ketone. Here we have 2 alpha positions. These are much better candidates for enolization. So we have 2 implied hydrogens on either side. So let's take our hydroxide and let's get one of those. Let's enolize over there. Boom, boom. So now we have our enolate. So an enolate is going to attack a carbonyl containing compound, but here's where the Michael addition comes in. A Michael addition is done where an enolate attacks an alpha beta degree of unsaturation, and it attacks at the beta carbon. So here we have alpha beta unsaturation. Here's the carbonyl carbon, alpha beta. So when you see a double bond in that position with respect to a carbonyl, that tips you off to Michael addition, right? This is the key structural feature that is telling us that this is a Michael addition. So what are we going to do? Let me erase that actually. Let's take the enolate, and it's going to reform the carbonyl, and this is going to attack the beta carbon. So, and it's because of the conjugation. It's in a conjugated position so that this can go here, and then we're going to go there, right? So we reformed the carbonyl there. Here is our new carbon-carbon bond, and then the rest is here. Boom, boom, boom. There's the pi bond, and there's our phenyl ring. Now, let's protonate real quick. So we're going to grab a proton from water. And now the last step here is called tautomerization. So this is just an isomerization. So when you have an enol, so this is called an enol. It's an enol because it's an ene and an ol, right? We have an ene and an ol, right? The ol is for alcohol and ene is for alkene. And it's an enol if the hydroxyl is on one of the carbons in the alkene, right? One of the carbons that is participating in the double bond bears a hydroxyl. So enols will have a tendency to tautomerize to yield the ketone. Okay, so we're going to go like this. The pi bond is going to grab that proton, and then this is going to swing over here. So it just kind of snaps shut, right? It's an isomerization. It's not actually a chemical reaction because we're not changing any, right? We're just shifting where the proton is. So it's going boom like that. And then that's how we get our dicarbonyl product. Okay, so this is a 1,4 1,5 rather. Well, it's it's alpha, beta, gamma, delta. Yeah, it's in the delta position, right? The second carbonyl is 1, 2, 3, 4 carbons away, right? So Michael additions are going to give us 2 carbonyls in this specific configuration, right? This has to be 1, 2, 3, 4 carbons away. And it has to be 4 carbons away because it's the alpha carbon on the enolate that does the attacking, and it attacks the beta position with respect to the other carbonyl because of this alpha beta unsaturation. So boom, boom, boom. That is what dictates the spatial relationship between the carbonyls on the product. And this tautomerization, right? This is the enol tautomer, and this is the keto tautomer. And generally speaking, thermodynamically, the keto tautomer will typically favor. There are instances in which the enol tautomer is favored. Like, for example, if that generates a phenol, right? If this pi bond being there is then delocalized through resonance in a pi system, in an aromatic system, then the enol would be preferential thermodynamically. But typically speaking, if we're just talking about an isolated enol there and then the keto form there, the keto form is going to predominate. It'll be preferential thermodynamically. So that's called tautomerization. This is the enol tautomer. This is the keto tautomer. And tautomerization is generally going to prefer the keto tautomer. So that is why the Michael addition gives us this dicarbonyl product. And so it's a 1,4 addition is what it is, because the addition starts, here's carbon 1, 1, 2, 3, 4. It's a 1,4 addition. So that is the Michael addition. It's very similar to the aldol condensation in that we're generating an enolate, and the enolate is attacking a carbonyl containing compound. The two differences are it is attacking not the carbonyl carbon itself, but actually the beta carbon due to this alpha beta degree of unsaturation, right? alpha, beta. It attacks the beta carbon. And so that's why we get this spatial arrangement. So that's part one. Part two is that we know that aldol condensations give us ketones, usually, or it could be an aldehyde, but carbonyl-containing compound with an alpha-beta degree of unsaturation. Here instead, it's a dicarbonyl compound. We have two carbonyls with this exact spatial arrangement. We have them this many carbons apart, not more, not less. Right? So when you see a dicarbonyl compound where the carbonyls are this many carbons away, right? It's a 1,4 addition, 1, 2, 3, 4. You know that that can have been formed by Michael addition. And then you just have to figure out which bond to retrosynthetically cleave, right? In this case, it would be that one, because this is stemming from what could be an enolate carbon, okay? So that is that one. Let me see if I missed anything. Lyndon asks, so is the wedge skeleton formed by the Diels-Alder reaction and dashed skeleton the original one? Is that from when I just went up here? So this, yeah, so this is like a separate question. This is the question if this diene reacted with the transdienophile. This one, as shown, is if it reacts, as we saw first, with the cisdienophile. And the dashed skeleton, the original one. I hope that answers your question. I'm not exactly certain if that's what you're asking. Asian Chopstick says, hey, Prof. Dave, could you explain to me Markovnikov's rule and anti-Markovnikov? Absolutely. So, yeah, I can do it right here. So Markovnikov's rule, let's say we're doing HBr. How does this addition reaction work? That pi bond grabs the proton, and we know that our intermediate is going to have a carbocation here. So that pi bond grabbed that proton, and it can either have left a carbocation on the secondary carbon or the primary carbon. And it will always be on the more substituted carbon because it's more stable. There's more hyperconjugation from neighboring carbon atoms. And so then the bromide will attack, and we get our Markovnikov product. So Markovnikov addition is when the group that is being added to the double bond goes to the more substituted carbon. So we had there was a secondary carbon and a primary carbon participating in the pi bond. The secondary carbon is more substituted. It's connected to more carbons, 2 instead of 1. And the bromine ends up on the more substituted carbon. So that is the Markovnikov product. If instead we did this in the presence of peroxides, we would get the anti-Markovnikov product. And so anti-Markovnikov addition is when the group being added to the double bond goes to the less substituted of the carbons that were participating in the double bond. So here, bromine was added to the primary carbon. That's what makes this anti-Markovnikov addition. Now, there are different reagents that make things go one way or the other. Here, the peroxides initiate a radical mechanism, and so we end up going by the more more stable radical intermediate as opposed to the carbocation intermediate. It's just a different mechanism. So it's not that you have a primary carbocation as an intermediate in the mechanism. That's not what happens. But all you asked was about the terminology. Markovnikov. So Markovnikov and anti-Markovnikov are talking about regiochemistry. We're talking about different structural isomers, right? Different regiochemistries yield different structurally isomeric products. So Markovnikov addition gives us the bromine. In this case, we're doing hydrohalogenation. Whatever the important group is that's being added to the pi bond goes to the more substituted carbon that was in the pi bond. Anti-Markovnikov, the group goes to the less substituted carbon that was participating in pi bond. That's what that terminology means. It applies to many different types of reactions. You can have Markovnikov hydration and anti-Markovnikov hydration. You can have, right, it's terminology that applies to many different addition reactions, but they apply to addition reactions. So you're adding two groups to the pi bond, one to each carbon. The more substantial one, the more important one, more substituted, less substituted, Markovnikov, anti-Markovnikov. Pavitt says, sorry, I missed a part of your explanation. Why does the double bond attack the beta double bond? Sure. Okay. So you're talking about the Michael addition. So it is simply the conjugation here. So there is a delocalization, right? That we could draw a resonance structure of the Michael addition electrophile, right? We could have a resonance structure where the pi bond, we have a formal positive charge on there. Let me see if I can find some room here. I could probably do it over here. So there is a resonance structure that looks like this, right? So if there is a resonance structure that looks like this, and we have the enolate attacking, right? Remember that the enolate has a resonance structure here where where it's a carbanion. So one of the resonance structures has a formally charged a formal negative charge on that carbon, and then that runs into this. One of the resonance structures has a formal positive charge on that beta carbon. So for reasons of electronics as well as sterics, this is the more sterically available position for a nucleophile to attack, but this is where it's going to go, right? It's going to go here because it has the capacity to push that pi bond over. So we usually don't use that. It's such a weakly contributing resonance structure, but it does inform the electronics of the electrophile. So that's going to go boom, and then that's going to go up there, kick that pi bond there, do that over there, right? So that's just how Michael works, Michael addition. Yeah, same question. So I would say it is actually more electrophilic because in both of these, right, this other resonance structure here, we see this carbon continuing to be neutral while this carbon has a formal positive charge. Again, that's only because of the alpha beta unsaturation. If the alpha beta unsaturation is not there, then the carbonyl carbon is the only site of electrophilicity. But because of that alpha beta unsaturation and this resonance structure that does contribute overall, this is that's a more electrophilic site, that carbon right there. Yeah, Danny has Markovnikov rule. That's another way of stating it, that the hydrogen atom will go to the carbon atom that's bonded to the most amount of hydrogen atoms. I don't prefer that definition, but it is correct, right? So, for example, here we reacted with HBr, and the hydrogen that we got from that went there. So this carbon already has two hydrogens. This carbon only has one hydrogen, and the new hydrogen went right now. This right. So this hydrogen is one of these hydrogens. So the new hydrogen went to the carbon that already had more hydrogens. So that's one way. If that's the way you want to memorize it, that's totally fine. I prefer to think of it in terms of the incoming nucleophile going to the more or less substituted carbon, but whatever works for you. Danny has to use HMNO4 to turn alcohol or aldehyde into carboxylic acid. That would be KM. That would be potassium permanganate, right? KMNO4. Potassium permanganate is that oxidizing agent that you are looking for. Yes. Okay. Moises asked for reactions and activators, deactivators. So I do have electrophilic aromatic substitution questions on this one. We didn't get there today, so we're going to get to it here. I'll show you, right? We have NMR, and then I was going to go right into electrophilic aromatic substitution. So we will start with that next week. And that's it. Yeah. So I was hoping to get to this NMR today, but we had a bunch of questions, so I wanted to make sure I answered all your guys' questions. But we'll start with this NMR. I know a bunch of you guys have been asking for some spectroscopy, so I'm going to load up some NMR, some IR, maybe some combos to try to identify molecules, and then we'll get into electrophilic aromatic substitution, because that's a very bulky unit. We do have to talk a lot about that as well. So we will start that next week. So yeah, once again, I'm partnering with Chegg here to bring you these office hours for Organic Chemistry 1, 5 p.m. Pacific every Tuesday. So I will see you guys next Tuesday. We'll continue where we left off. Make sure you check the QR code, see what other courses you can get some help with, and we're going to